and welcome to the 12th lecture of CS2100 District Structures course. So in this lecture, we'll talk about a couple of properties of functions that we'll also formalize, and then we'll show how to do simple proofs that prove these properties about example functions. So let's get started. Okay, so what are these properties that I mentioned in the title slide? So the first one is called onto, then we have one-to-one and one-to-one correspondence. So a function is onto if every element in the codomain is the output of some element of the domain. We can also write this as function f that maps A to B is onto if and only if for all elements B in B there exists an element A in A such that B is equal to f of A. So you can think about this property as all elements of the codomain have to be used up. Note that that is already true for the domain because that is required from functions. Okay, so then a function is one-to-one if nothing in the codomain is an output via two different inputs. So if you think about an arrow diagram, this means that there are no more than one arrow incoming into some element in the codomain. We can write this more formally as f that maps A to B is one-to-one if and only if for all xy element of A, if f of x is equal to f of y, then x is equal to y. Okay, and then a function is one-to-one correspondence if it's both one-to-one and onto. So here are three example functions, and we'll try to determine their properties. So let A be equal to A, B, C, D, E, and the domain is the domain of each function. And let B be the set of letters in the alphabet and the codomain of each function. So the first question is, are any of these functions onto? So remember, onto means that something gets mapped to each element of the codomain. So the answer to this is clearly no. Because codomain is a set of all letters in the alphabet, and domain has only 5 elements. So there will definitely be elements of the codomain that nothing is being mapped to. Is any of them one-to-one? So let's see F first. Okay, we have both A mapped to R and D mapped to R. So it's not one-to-one because we have two elements of the domain being mapped to the same element in the codomain. Let's look at G. Again, we have A is mapping to Z and E is being mapped to Z, so it's not one-to-one. What about H? So H is one-to-one. Because there are no elements in the codomain to which more than one element of the domain is mapped to. Okay, so we determine these properties of an example function. So in the last lecture, we talked about function inverses. And now we can define a related property called invertibility. So a function f that maps A to B is called invertible if there exists an inverse function. That is, if there exists a function called f minus 1 such that f of x is equal to y if and only if f of minus y of y is equal to x. So here we can also say that f of minus 1 is equal to f, and f of minus 1 of y is equal to y, and f of minus 1 of f of x is equal to x. Note that this is equivalent to saying a function has one-to-one correspondence, meaning that it's both onto and one-to-one. So if you can prove that the function is both onto and one-to-one, then you know that the function is invertible, so that there exists an inverse of the function. So this also indicates that, as we already saw in the last lecture, that not all functions have inverses. So let's look at the two examples. So recall these two functions. So let B be the set of binary strings of length 5. And the codomain is set A of numbers 0, 1, 2, 3, 4, 5. And rule is that f of B is equal to A. The number of ones in the string B. So f maps the number of ones in the string, looks at B, counts the number of ones, and maps that to A. So is this function invertible? So first, we have to show that it's onto. We have to think whether it's onto and then whether it's one-to-one. So is it onto? So is something going to be mapped to every element of A? The answer is yes. Because there'll be a string 0, 0, 0, 0 that's going to map to 0, all ones that is going to map to 5, and everything in between. Is it 1 to 1? So the answer is no. Because there'll be binary strings that will map to the same element of the codomain. For example, there can be a binary string that starts with 1 and has all zeros, and the binary string that ends in 1, and everything is all zeros, and both of these are going to be mapped to 1. So it's not one-to-one. And then another function, domain is 0, 1, 2, 3, 4, 5. B is the set of binary strings. And the rule is G of S equal to B, where B is the string consisting of A ones followed by 5 minus A zeros. Is this function invertible? Okay, so is this function onto? The answer is no. Because there is nothing that is going to map to, for example, 0, 0, 1, 1, 1. It's always going to be ones followed by 0. So it's not onto. So neither of these two functions are invertible. Okay, so now let's look into how we do onto and one-to-one proofs. If we have a claim or a proposition that function f is onto, how do we prove it? So here is the sketch. So we start with assuming that some b, element of b, is given to us. And then we have to use known information about f to demonstrate there is a domain element a, element of a, such that f of a is equal to b. So that's the structure of the proof that you always follow to show that the function is onto. So let's do an example onto proof. So we have a function g that maps rationals to rationals, and the rule is that g of x is equal to 5x minus 1. We want to show that it's onto. So let's follow the structure that we defined in the previous slide of the proof. So we assume that some y that is a rational is given to us. And from there, we want to show that there is some x in the domain that maps to this y. So let's take this x to be y plus 1 divided by 5. And you can actually easily derive this from the rule of g. Okay, so we pick this x. So first we have to show that x belongs to the domain. That's easy to show. So since y is a rational, when we add 1 to y and divide it by 5, we are going to get a rational because rationals are closed under addition and division. So it follows that x is indeed a rational, which means that it's element of domain. So that's the first thing we have to show. And the other thing we have to show is that x maps to y. So we do this by computing g of x. So g of x, we plug in what x is, we work out the numbers, and we get that g of x is equal to y. So hence, we show that for any chosen y in the codomain, we can pick some element of the domain such that y is going to be its output. And so g is onto. And that concludes our proof. So I would say the trickiest part here is to pick this x. But you can easily do that by deriving it from the rule. Okay. Now let's look at the recipe for doing one-to-one proofs. So the claim of the proposition is that function f that maps a to b is one-to-one, and we want to prove this. So the structure of the proof is that we assume that a1 and a2, that are element of the domain A, are given to us such that f of a1 is equal to f of a2. And now we have to use known information about f to demonstrate that a1 is equal to a2. So let's look at an example proof. So our proposition is that function f that maps integers to integers with the rule f of x is equal to 5x plus 7 is one-to-one. So let's do this proof. Let integers x and 1, x1 and x2 be given such that f of x1 is equal to f of x2. So we follow the structure of the proof that we introduced in the previous slide. Okay, so if f of x1 is equal to f of x2, then we know that 5x1 plus 7 is equal to 5x2 plus 7. So here we subtract 7 from both sides. So 7 and 7 cancel each other. We get that 5x1 is equal to 5x2. Now both sides are divisible by 5. And the division theorem says the quotient must be unique. From that it follows that x1 is equal to x2. And so f is one-to-one. So here we divided both sides by 5. So that concludes the proof that f is one-to-one. Okay, in the next couple of slides, we'll connect set cardinality of the size or the size of the set with these properties of functions we just introduced. So the first theorem that we introduced says that let f that maps a to b be a function where a and b are finite sets of sizes m and n respectively. Then, if f is one-to-one, then m is less than or equal to n. If f is onto, then m is greater than or equal to n. And if f is a one-to-one correspondence, then m has to be equal to n. Okay. we can sketch a quick proof of one of these properties. So let f that maps A to B be a function where A and B are finite sets of sizes m and n respectively. And then we're doing a contrapositive of one of the claims on the previous slide. So if m is greater than n, then f is not one-to-one. So we can easily see this from the pigeonhole principle. So if m is greater than n, then we know that there will be boxes. So we have n boxes. So these are our elements of the codomain. And now we are distributing m elements of the domain into these n boxes. And given that m is greater than n, there will be at least one box that has more than one element. And because of that, f is not one-to-one. So that's a simple proof, a sketch of a proof of one of the claims from the previous slide using pigeonhole principle. So we are not going to prove the others. I just want to give that as an example. Okay. If you remember, a function f that maps A to B is called invertible if there exists an inverse of the function. And also if it's both onto and one-to-one. Now, if we connect that to the set cardinality, sets A and B have the same cardinality if there exists an invertible function f that maps A to B. We also know that set A is infinite if there exists a function f that maps A to A that is one-to-one but not onto. For example, the set of natural numbers n is infinite. And we know this because we can pick a function f that maps natural numbers into natural numbers. And we define it with the rule f of x is equal to 2 of x. So clearly, it's one-to-one. So if you multiply x by 2, you will never have two x's that map to the same number. We can actually also prove this. But it's not onto because it's going to leave holes. For example, nothing is going to map to the number 3. And so this is a really simple proof that a set of natural numbers n is infinite. So it's kind of interesting how we can leverage properties of functions to prove that some set is infinite. This also leads us to two important theorems. We're not going to prove them. I'm just going to state them. They're kind of interesting. So the first one is a Cantor-Bernstein theorem. It says that given sets A and B, if there is a one-to-one function f that maps A to B and a one-to-one function g that maps B to A, then sets A and B have the same cardinality. So this is a helpful result because sometimes finding an inverse of a function can be difficult. And using this, we can, for example, show that A is infinite, B is infinite as well. Cantor's theorem also states that for every set A and P of A do not have the same size. So these are kind of two important theorems that are interesting to remember and to know. And with this, I conclude part 1 of this lecture. And we'll move to part 2 next.